Okay. This week's speaker is Emilio Minichiello. He graduated from CUNY and currently works for Kinexus AI. His thesis was on something related to what he's talking about today, so I'll let him go. Emilio, thanks for coming and
Yeah,
tell us about your talk.
yeah, thanks for having me. So today I'm going to talk about diffeological spaces, which occupies what I think is a really nice place in the categorical differential geometry world, which is a small world, but growing. Let's see here. Okay. So yeah, I'm Emilio Minichiello. I recently graduated and defended my PhD thesis at the CUNY Graduate Center in New York City. My PhD thesis is about using categorical homotopy theory to study diffeological spaces. All right, so what is diffeology? Why is it useful? Why am I here? Why am I blabbering to you all about it? So here are the table of contents. We're going to talk about diffeological spaces, some constructions you can do with them, some ways in which they fail to be like smooth manifolds. And then I'm going to talk about connections with higher topos theory and sheaf theory. So why diffeology? I have to motivate this, right? So let man denote the category whose objects are finite dimensional smooth manifolds and whose morphisms are smooth maps. This is the category that, differential geometers have been working in for many, many years. This category sucks. It doesn't have all limits, doesn't have all colimits, it's not Cartesian closed. Um, it has finite products. It doesn't even have coproducts, though. You take a three-dimensional manifold and you take the disjoint union with a five-dimensional manifold. It's no longer a manifold technically. Um, you can't just quotient a manifold and expect it to be a manifold. You can't take a subspace of a manifold and expect it to be a manifold. So yeah, category theorists should be nauseated by this category. Um, Now, you all should know category theory, I hope. But if you don't know much category theory, you can think of it this way. You can consider the union of the x-axis and the y-axis in R2, and we call it axes. So this is the result of taking two copies of the real line and gluing them together at the origin. Um, this isn't a manifold, right? So at every point, it's one-dimensional, except at that origin point. It looks two-dimensional almost. Um, so it's not a manifold. For the last 200 years or so, an astonishing amount of theory has been developed for good old finite dimensional smooth manifolds. These involve elaborate constructions and powerful theorems, but none of them apply to our friend, the axes space. So here's the idea that I want to try and get across for why diffeological spaces. So what I want as a category theorist is to find a category C such that man embeds into it. There's a fully faithful functor from man into the category, but that's not enough. There's lots of stupid ways you could do that. You could use the Yoneda embedding and go into pre-sheaves. So number one's easy. Number two is the hard part. We want to extend our classical theory to this new category. I want to do constructions from differential geometry and extend it to this larger class of smooth spaces, right? So that's the sticking point. So diffeological spaces are a solution. I'm not claiming they're the only solution to one and two. Synthetic differential geometry is another solution, but it has a much, much different flavor. Um, so yeah, I'm not going to talk about that. We can, but yeah, let's just focus on diffeological spaces. All right, so what are they? Um, so as I said, the category diff of diffeological spaces is one such choice for C. This is our category that we want to think of as generalized smooth spaces. So first of all, we say a manifold U is a Cartesian space if it's diffeomorphic to Rn for some n. So n isn't fixed here. Could be R0, a point, could be the real line, R squared. If X is a set, then we say a function from a Cartesian space into that set is a parametrization, as long as U is Cartesian. We say a collection of subsets where each UI is Cartesian is an open cover if, you know, the union of all the subsets equals U. Now, a diffeological space consists of a set, X, and a collection of parametrizations satisfying three axioms. So first of all, you want D to contain all the points. Okay, so every point of X should be in this collection. And if I have P and it's in D, and I have a smooth map from another Cartesian space into U, then I want the composition to belong to D. So I want to be able to precompose by smooth maps. Now, if I have an open cover of U, and I have a parametrization into X, such that when I restrict to each open subset in that open cover, if that restriction belongs to D, then the parameterization P had better belong to D. So these are the three axioms that define a diffeological space. So a diffeological space is a set and a collection of parametrizations. We call the collection D here a diffeology on X. And the elements of D we call plots. So you can think of this kind of like in differential geometry of charts. And these are like homeomorphisms from Cartesian spaces into your manifold. But here, you know, P is a set function. There's no topology anywhere. So this is a really wild and big collection normally. Okay, any questions on that? Cool. All right. So similarly to topology, any set can be given two canonical diffeologies, the discrete diffeology and the indiscrete diffeology. The discrete one consists of all the constant maps. So any map that factors through a point, you can check that's a diffeology easily. And the lower bullet, the indiscrete one, just consists of all the parametrizations. All right. Now, that's fine, but what we really care about is smooth manifolds and extending them. So every smooth manifold had better be a diffeological space. And indeed it is. So if you have a finite dimensional smooth manifold M, then the collection of functions from a Cartesian space into M such that P is smooth in the classical sense, that forms a diffeology. So if I have a Cartesian space, I have a manifold, I know what it means classically for that map to be smooth, for that function to be smooth. Yeah, that forms a diffeology. We call that the manifold diffeology or the canonical diffeology of the manifold. So every manifold is a diffeological space in this nice canonical way. And the set associated to is the underlying set of the manifold. Now, if I have two diffeological spaces and I have a set function between them, I say F is smooth if for every plot of X, the composite function is a plot of Y. Now, if you contrast this with the definition of a smooth map in classical differential geometry, I think this is such a nicer definition, so much easier to work with. Now, proposition, I should say also that the subject was initiated by basically one person, Patrick Iglesias Zamor, he and his advisor, Soryu, came up with diffeological spaces in the 80s, in the late 80s. But Iglesias worked on it kind of by himself, maybe with a couple other people for decades. There wasn't a lot of activity. And there was no category theory involved. This was all done in a kind of ad hoc fashion. But in 2013, Patrick Iglesias Zamora wrote a textbook called Diffeology, and I highly recommend people check it out. It might seem a little granular or a little, differential geometry focused for category theorists, but there's mention of category theory, and you'll recognize all the categorical stuff. Anyway, here's the proposition. This is from his textbook. So if I have two finite dimensional smooth manifolds and I have a function between them, that function is smooth in the classical sense if and only if it's smooth as a map between their associated diffeological spaces. In other words, the functor that takes a manifold to its canonical diffeology is fully faithful. All right. Now, so we've seen that every manifold is a diffeological space in this really nice way, but there are some real big differences between diffeological spaces and manifolds. So if I have a diffeological space in a subset A, then A inherits a canonical diffeology. A parametrization, P from U to A, is a plot of A if the composition, where I first do P and then I include it into X, if that's a plot of X. We call this the subset diffeology on A. So if you have a random subset of a smooth manifold, there's no guarantee it's going to be smooth manifold. But for diffeological spaces, the subset, there's always a diffeology. Similarly, if I have a diffeological space X and I have an equivalence relation on X, then I can take the set quotient of X by that equivalence relation. And then there's a canonical diffeology I can put on that quotient. So a parametrization P into the quotient is said to be a plot if there exists an open cover of U and plots of the unquotiented space such that this diagram here commutes. And you can check that this forms a diffeology. And we call this the quotient diffeology on the quotient set. Cool. So we've got subsets, we've got quotients. Now, if I have two diffeological spaces X and Y, then we can consider the set of smooth maps between them in the sense that I told you before, where it takes plots to plots. This forms a set, and this inherits a diffeology called the functional diffeology. So how do you define this? So if I have a function of a parametrization from U to the set of smooth maps, I say it's a plot if when I take as a set function, if I uncurry the map, then I have a set function from U times X to Y. Now I haven't explained how you do this, but you can easily put a product diffeology on the product of two diffeological spaces. You just take pairs of plots, and U is a manifold, so it has a canonical diffeology, and X is assumed to have a diffeology, and Y is assumed to have a diffeology. So now I have a function between two diffeological spaces, and I know what it means for them to be smooth. So I say P is a plot if this other uncurried map is smooth as a map of diffeological spaces. Okay. So diffeological spaces are closed under subsets, quotients, and mapping spaces. And this is wildly untrue for smooth manifolds. Everybody all right with that? All right. So what else can we do with diffeological spaces? We have a category, diff, and it turns out to be extremely nice. It has all limits, co-limits, and is Cartesian closed. It also receives a fully faithful embedding from the category of smooth manifolds. But now there's that nagging second part of our question. How do we extend our classical constructions in differential geometry, such a vast generalization? All right, so first let's talk about topology. I haven't mentioned topology yet. You don't need to put a topology on the set to define a diffeology for it. This is very different than smooth manifolds, where you always assume first I have a topological space and then I put a smooth structure on it. Here we haven't done that. In fact, if I have a diffeological space, it inherits a topology. Okay, so we call this the D topology. We define it as follows. If I have a subset A of X, I say it's D open if for every plot of X, the inverse image is open in U. And this makes sense because U is a Cartesian space that has a canonical topology. I know what it means to be open in U. Okay. So this defines a topology on X. And the collection of topological spaces that arise from the D topology of a diffeological space are called delta-generated topological spaces. And they're a really interesting class of topological spaces. For instance, they're all locally path connected. And they fit into this nice story about convenient categories of topological spaces. Because the category of topological spaces kind of famously isn't Cartesian closed because annoying technical reason. So there's all these different candidates for more convenient categories of topological spaces. And these delta generated ones are one such candidate. We can also define differential forms. So if I have a diffeological space X, a differential form on X consists of a collection of differential forms on every plot, such that if I have a map of plots, so I say F, which is a function between V and U, so the domains of the plots, I say this is a map of plots if this diagram commutes. So P is a plot, Q is a plot, F is a smooth function. I call that a map of plots. So basically, I have these differential forms sitting on the domains of every plot here, and I want them to be compatible. So if I have a differential form on U, I want to be able to pull back that differential form to V, and I want that to be equal to the differential form I have on V. Any questions on that? So once we have differential forms on a diffeological space, we can define the de Rham cohomology. So de Rham cohomology is basically just the cohomology of taking differential forms, and they have D, which you can think of as taking the derivative, and this forms a cochain complex, and you take the cohomology and you get a cohomology ring, a graded ring for any diffeological space. And this cohomology is really interesting. So for instance, here's a non-trivial diffeological space. So what you can do is take alpha to be an irrational number and consider the following group. It's the group of integers of the form n plus alpha m, where n and m are integers. So this forms a subgroup of R, but it's not a Lie subgroup. It's actually dense in R. So you can imagine it's filling up R topologically. So R has its canonical diffeology because it's a manifold, and then um, Z plus alpha Z, you can just give the discrete diffeology, and you can embed that into R. And then we can take the quotient. So we take R mod Z plus alpha Z. And then, as I said before, you get another diffeological space. So when I take this quotient, I get what's called the irrational torus. And this is like the example of diffeological spaces. It's what Patrick Iglesias Zamor studied originally. It was like the main example for a very long time, and still kind of the main example of diffeology. And the reason for that is because its D topology is coarse or codiscrete. In other words, the only open subsets are the empty set and the whole set. So the topology is really boring. It's really boring, and there's no tools in algebraic topology that'll tell you anything interesting about a space like this. However, in diffeology, it's non-trivial. So its de Rham cohomology is non-trivial. So it has R in degree 0, because it's connected. In degree 1, it's R. Okay. And in higher degrees, it's 0. But this is quite surprising in some sense. So somehow the diffeology sees more about this space than its topology does. And we can get interesting information about this space from its diffeology.
When you're calculating those cohomology groups, do you need to use any special methods because or does standard approaches work?
So it's actually really interesting if you look at how Patrick computes this stuff in his book. Patrick does everything very low level by hand. So especially these computations. Basically, what you do is you show that the differential forms, like everything's closed. So then D is like 0. And then you have to do like a little bit of an argument about its dimension and stuff, and then it kind of just falls out from that. But as I'll talk about later, there are like pretty fancy methods you can also use to get at this. But for this specific example, it's quite easy to actually just do it by hand.
Nice.
Yeah, good question. All right, so the following notions have also been defined in diffeology, and they're detailed extensively in that textbook I was telling you about. So you have covering spaces, you have universal covering spaces, fiber bundles, principal bundles, homotopy groups. So these are things that we really, really care about in differential geometry. And I can define them for any diffeological space. I know what all of these words mean, thanks to years of work by Patrick Iglesias Zamora. So furthermore, every diffeological fiber bundle induces an exact sequence of diffeological homotopy groups. So this is something we would expect for smooth manifolds or topological spaces that are like CW complexes. So we also have this. And again, when we talk about the homotopy groups here, we're not talking about the homotopy groups of its underlying topological space. We're talking about like a smooth version of homotopy groups. So you can also compute the homotopy groups of the irrational torus. And this you can read off from the exact sequence. That's how you compute these. So in degree 0, it's trivial, and then in degree 1, it's z squared. So that's kind of like a torus. A torus, the fundamental group is also z squared. You have a hole going around horizontally and vertically. So that's something interesting that kind of persists. So we've seen how to extend these kind of classical constructions from differential geometry to all diffeological spaces. But we shouldn't expect all our favorite theorems to hold, right? We're extending from a very particular class, smooth manifolds, that have a lot of really nice properties, and we're extending it to a much wider class. So even though we're able to come up with constructions, and those constructions agree with the classical versions on the smooth manifolds, we shouldn't expect that a lot of our favorite theorems hold on these constructions in general. It's just too optimistic. And this is mathematics. Should never be that optimistic. So let's talk about the failure of some of these classical results. All right, so if I have a diffeological space in a point, I get a category. It's plot category. It's pointed plot category. And the objects are smooth maps, where U is an open connected subset of Rn that includes the origin of Rn. So you can imagine this U is not necessarily Cartesian. It could have some topology, but we want it to be like based around the origin, like that. And we want it to take the origin to X. And the morphisms of this category are going to be maps between the domains that send the origin to the origin that make the triangle commute. So this is a nice category you get for any pointed diffeological space. And then there's a functor, T, from this plot category to vector spaces. And this takes one of these smooth maps to the tangent space of U at the origin in the classical sense, because U is a manifold because it's an open subset of Rn, so it's automatically a smooth manifold. So it makes sense to say what a tangent space is at 0. And then there's also a functor, pi, that takes from the plot category to the category of pointed diffeological spaces, that takes a smooth map from U to X and just gives you the domain U with the point at 0. So I have two functors out of this plot category. So we're category theorists, so we take the left con extension along this functor. We know vector spaces is co-complete, so we can take this left con extension. It always exists. And this defines what we call the internal tangent space of X at the point little x. So this is a vector space. And this actually turns out to agree with the usual tangent space when X is a manifold. That's non-trivial result. But if you actually look through the definition, it's not super hard to prove. It's actually kind of reminiscent of how you think about the tangent space as equivalence classes of curves at this point, X. But it's defined for all diffeological spaces. And it was actually studied in 95, but it didn't really get its modern definition until Christensen and Wu wrote their paper in 2015. And I think it's one of the best papers in diffeology, actually, this one, where they define this internal tangent space. Turns out there's also a notion of an external tangent space defined in that same paper. And it's the vector space of smooth derivation on germs of smooth functions from X to R. If you don't know what that means, don't worry about it. You think of it basically as like, I take a function from X to R and I look at it like at the point, and I take an equivalence class of that. So instead of maps from R into X, which is like the internal one, I have maps from X to R. Okay, so these are two different notions. However, in classical differential geometry, something you learn in a first course of differential geometry, you prove that these two notions of tangent spaces are actually equivalent. They're isomorphic as vector spaces whenever X is a smooth manifold. But in diffeology, this isn't true. So there are diffeological spaces where the internal and external vector spaces, tangent spaces, don't agree. The irrational torus is an example. So this is from Christensen Wu's paper. At any point, the internal tangent space is R, but the external tangent space is R0. So this is telling you something quite interesting and something completely new that you don't see in classical differential geometry. So somehow mapping into the irrational torus is easier somehow than mapping out of it, right? Because the internal tangent space is looking at maps into it, externals maps out of it. So another sacred result of classical differential geometry is the isomorphism between Čech cohomology and de Rham cohomology on smooth manifolds. And if you want to learn more about cohomology of smooth manifolds, you should read Botten 2's book. I think it's like differential forms and algebraic topology, something like that. It's an excellent book. And the proof of this theorem is super easy once you develop a bunch of machinery like spectral sequences. Once you understand spectral sequences, you can prove this argument like incredibly quickly, like less than a page. But I guess you need some bit of the page to actually show the spectral sequence. So it's actually shorter than that. Anyway, so Patrick Iglesias Zamora proved using his own version of Čech cohomology. So remember, every time I say like Čech cohomology of a diffeological space, this thing has to be generalized from the classical definition. So what Patrick Iglesias did was he came up with a Čech cohomology for diffeological spaces, and then he proved that his Čech cohomology on an irrational torus is R squared, but the de Rham cohomology is R. So that means this beloved isomorphism doesn't hold for diffeological spaces. In fact, more is true. You can actually pick out the actual obstruction to these groups being isomorphic. So here's his big theorem. For any diffeological space X, there's an exact sequence here. So here's the first de Rham cohomology group. Here's the first Čech cohomology group that he defines. I call it the PIZ Čech cohomology. And this R delta here just means R thought of as a discrete abelian group. Okay, so it's not, don't worry about it, it's just notation. This group I'll explain in a second. And then here's the second de Rham cohomology, and here's the second Čech cohomology. So you get this nice exact sequence. All right, so if this thing was 0, then being exact would mean that this is an isomorphism, this map, and it would mean this map is injective, right? So and this being 0 means in degree 1, the Čech de Rham isomorphism holds. But if we can prove that for X, this is non-zero, then this map is not necessarily an isomorphism. Okay, so what is this thing? This thing is the group of isomorphism classes of diffeological R principal bundles that admit a connection on X. Now, classically, if X was a smooth manifold, every principal R bundle on it is trivial. It's isomorphic to X times R over X. But for diffeological spaces, that is not true. There are non-trivial R principal bundles. And they can admit connections, which I won't speak too much about. But yeah, this when I plug in a smooth manifold here, this thing is 0. And that proves the Čech de Rham isomorphism in degree 1 for smooth manifolds. Obviously, it doesn't prove it for the higher groups, but it proves it in degree 1. Okay, so what is this map C1 here? This is the curvature of the connection. So a connection is a 1 form, and then you can take D of that, and you get a 2 form, and you can take its cohomology class. And yeah, if this map is 0, then these are isomorphic. So again, the irrational torus, it's been proven that this thing is non-zero for the irrational torus. And as we saw before, these are not isomorphic. So what I did for my thesis was I extended Patrick's result from dimension 1 to all dimensions. And I'll talk a little bit more about how I did that. But what's funny is that when you go up higher in dimension to k greater than equal to 1, you actually get 2 exact sequences. So before, so here, yeah, here's one of them. So I'll explain what this notation is in a second. This is my version of check cohomology for diffeological spaces. Here's another version of like of bundles with connection, but these are called R bundle gerbs. Okay, so I won't exactly explain what those are, but you can think of them as like higher dimensional versions of bundles, where dimension here means like cohomological dimension or something. So in other words, principal bundles define cohomology classes in degree 1. R bundle gerbs classify cohomology in higher dimensions, higher degrees. And then you have Deram and check again, and you get this exact sequence. But you also get another one. And here notice that instead of Deram cohomology, I just have the closed forms. So this term here is R bundle k minus 1 gerbs with connection, and then this guy is R bundle k minus 1 gerbs with a choice of curvature form. Okay, so if you don't know what this means, don't worry about it. I'm just showing you that things are a little bit more complicated for diffeological spaces than for smooth manifolds, and you get this very interesting structure. All right, so now let's talk a little bit about higher topos theory and sheaves. So we've already seen how nice the category of diffeological spaces is, especially when you compare it to the category of smooth manifolds. But this should make us a little suspicious. Where's all this niceness coming from? It's not every day that you ad hoc construct a category and it's that's nice, right? So here's a theorem. This is Baez and Hoffnung, his student in 2009. They prove, amongst other things, that the category of diffeological spaces is equivalent to the category of concrete sheaves on the site of Cartesian spaces. So I have this equivalence. So Cart is the category whose objects are Cartesian spaces. So these are spaces diffeomorphic to some Rn, and then smooth maps between them. And then I give it a Grothendieck topology by declaring that a collection of maps into some Cartesian space U is a covering if there are a bunch of inclusion of open subsets that give you an open cover. So once I've defined the site structure, I can define sheaves on the site. And then I can look at the full subcategory about what are called concrete sheaves. So the category of sheaves on Cart is as nice as it could be. It's a Grothendieck topos. The concrete sheaves, they don't form a Grothendieck topos. They form what's called a quasi-topos. But quasi-topoi are extremely nice categories. They're almost as nice as growth and topoi. So we've lost growth and topos niceness, but we've got something very close to it. And I'm not going to give the definition of a concrete sheaf. You can just look it up on the MLab or something. But basically, the idea is that it's a sheaf where you have a good notion of underlying set. Okay. So like, for example, the differential forms like omega K, that forms a sheaf on cart, but it's not concrete. But every smooth manifold is a concrete sheaf, and every diffeological space by this theorem is a concrete sheaf. So how do you think about this? Well, a sheaf is a functor from cart op into set. So if I have a diffeological space X, what's the sheaf? Well, it takes a Cartesian space U and gives you X of U, which is a set. What is that set? Is the set of plots with domain U of X. So it's this equivalence is very, very simple and straightforward. And I highly recommend you guys look at this paper by Baez and Hoffnung. It's super well written. I should say that if you look at it, this statement is not in that paper. They use a different underlying site called the open subsets of Rn rather than Cartesian spaces. But I proved in my thesis, and it's very easy to prove that these categories are equivalent. I find it a little bit easier to think about Cartesian spaces rather than open subsets of Cartesian spaces. Okay. Now, this connection allows for a really nice, exciting new perspective on diffeological spaces. For example, a differential form, which I told you how to define before, kind of a hands-on definition, that's exactly the same thing as a map of sheaves. So X is a sheaf. In fact, it's a concrete sheaf. Omega K is a sheaf, but not concrete. But I can still consider them in the category of sheaves and look at a map between them as sheaves, right? And that's exactly the same thing when you unravel the definition as what I defined before. So for every plot, you have a differential form and they glue together. And that's exactly what it means to have a map of sheaves here. So in my thesis, I explore this connection even further. Instead of just thinking of sheaves of sets, I consider sheaves of spaces. And when I say space, I'm really thinking homotopy type, simplicial set. Okay, but it doesn't really matter. So the study of sheaves of spaces, also called higher sheaves or infinity stacks, they have all kinds of crazy names. The study of this is called higher topos theory, and it blends classical sheaf theory, category theory, and homotopy theory together into a really beautiful subject. And higher topos theory is a very, very powerful framework to work with for differential geometry because it allows you to define and manipulate exotic cohomology theories. So often what you'll see in the literature is somebody works really, really, really hard to define some notion of cohomology, like differential cohomology. And it's really unwieldy, and you have to be a subject expert to even understand what the hell you're talking about. But higher topos theory gives you a framework to manipulate all different kinds of cohomology. So here's a very rough idea. I can explain more afterwards, but an infinity topos, H, you can think of as a really nice space-enriched category. So like an infinity category. And you can think of it as a category of sheaves of spaces on some site. So you can even take just a normal definition of a site, a category with a growth and topology. You can think of that as an infinity category trivially. And then you can take sheaves of spaces on that site. Okay. So if I'm inside of an infinity topos and I have two objects, X and A, then because this thing is space enriched, we get a space H of X and A that you think of it as like the Hom space, the mapping space between X and A. And when I take the connected components of this space, I get a set. And I call that the zeroth infinity stack cohomology of X with values in A. Okay. So basically the Hom here is playing the role of cohomology. Now, that's good for degree zero. Degree zero works for any arbitrary two objects. But if I want higher cohomology, I can't just pick any old A. Higher cohomology doesn't exist for all choices of objects A, all coefficient objects. Only those that can be delooped. So you have some object A, and there's some operation called delooping that exists for some kinds of objects in the infinity topos, and you obtain this is what I call B upper K of A. So this is the K-fold delooping of A. So when I deloop it once, it's B of A. I deloop it twice, it's B squared of A, and so on. And this is how I define higher infinity stack cohomology, like this. And I should say that doing this in the appropriate way, in the appropriate contexts, for example, if I take the infinity topos to be the infinity topos of spaces, thought of as simplicial sets, homotopy types, however you want to think of it, this gives you singular cohomology. So when A is in a abelian group, this K-fold delooping is the same thing as the Eilenberg-MacLane space in degree K. Or like if this was N, it would be called like a KAN space. And then it's well known that the homotopy classes of maps from X into these spaces give you singular cohomology. And that's exactly what's going on here. Now, using this technology, one of the main results of the first paper in my thesis shows that if I have a diffeological group G, then diffeological principal G bundles, as defined classically in Patrick's book, his textbook, are actually classified by infinity stack cohomology. And this K should be a 1. That's a typo. So degree 1 cohomology of X in degree with a coefficient G is the same thing as the group of isomorphism classes of diffeological principal G bundles on X. Now, this is true classically, and it's also true for diffeological spaces. Now, this automatically defines, this is just what I said. And this group that I've defined here is closely related with non-abelian Czech cohomology groups of these two other papers. So another paper in the diffeology literature also defines an H1X of G, where G is non-abelian, but only H1. And they do it in a little bit more of an ad hoc way, and they show this isomorphism also, but they do it by hand. They show it by hand. My proof of this is I put a diffeological space into this machinery. I, turn the crank, and out pops the theorem. No hard work involved. And I think this connection between diffeology and higher topos theory, it's begun to bear fruit. My thesis proves that, but I think there's much more to explore. And I should say also that the way I prove this theorem, this these two exact sequences is completely internal to the infinity topos. So what do? I take a diffeological space. I think of it as a sheaf of spaces in a trivial way. I do something called cofibrant replacement, and then I map it into a bunch of other sheaves. So this is the sheaf where I deloop. So I can take R with a discrete diffeology. I can deloop it K times, and that gives me a sheaf of spaces. And then I map X into it, and I get a space, and I take pi 0, and that gives me this cohomology group. And that's what I do with all of these. And once you understand how all the pieces are in place, this theorem just pops out of the machinery. So yeah, I think this is a really nice idea, and I think it can be used in all kinds of places. And I think there's a lot more to explore. Thank you very much. That's the talk.
Very nice. All right, everybody, ask questions if you have them.
Yes, I have a very simple one. What do you need to add to the definition of diffeological space to obtain a smooth manifold?
What do I need to add to the definition of diffeological space to get a smooth manifold?
Yes.
Yeah, you say I have a diffeological space such that it's locally diffeomorphic to Rn. So for every D open subset, there's a diffeomorphism between Rn and that open subset, and then it has to be Hausdorff and second countable, the underlying D topology.
Okay.
That's equivalent to being a smooth manifold.
Okay. So the coproduct of diffeological spaces, you take the disjoint union, right, of the sets, and you take all the plots, right?
No, it's more complicated.
Okay, it's more complicated than this.
Yeah. So for pre-sheaves on cart, it would be exactly what you just described, right? Because you just take co-products object-wise. Now for sheaves, what you do is you take that co-product object-wise and then you sheafify. But sheafification is hard to understand, so it's not a very explicit process. Then for diffeological spaces, it's not enough just to be a sheaf, you have to be concrete. So you also have to concretify. So you sheafify and then you concretify, and that gives you colimits in diffeological spaces. But there's an easier way to manipulate colimits in diffeological spaces. You can see it in various papers and stuff. I can't think of a reference off the top of my head, but it sounds difficult, but it's not so bad.
And also, I don't understand why if you take a smooth manifold of dimension 2 and one of dimension 3, you don't have the coproduct like you say. Maybe it's very simple, but I don't know. What is the issue?
Right.
Yes.
So it's just a technical point. Technically, as a smooth manifold, every chart has to have the same dimension. So if
yeah.
So if you wanted, you could define a smooth manifold to be something such that every connected component has constant dimension, and then yeah, that would be the co-product in that category. The small technical thing.
Okay.
I think it's kind of an interesting point, because typically differential geometers work with this constant dimension. So, so they're working in this category. It doesn't even have co-products, it doesn't even have binary co-products, So.
Yeah. Okay, fine.
Okay, we'll go ahead and stop the recording there.